So, in this session we will be discussing about the tubular reactor with heat exchange, that is non-adiabatic, non-isothermal tubular reactor. So, it is tubular reactor PFR with heat exchange. See, so it is Fa naught, Fb naught, Fc naught, etc. Here whatever is moving out is Fa, Fb, Fc, etc. And its enthalpy HA, HB, Hc. Here it is HA naught, HB naught, Hc naught. Temperature commonly is T naught. Here it is T at L. So, this is Z equal to L, this is Z equal to 0. And it is operated countercurrently with coolant, say co-currently with coolant, and let us say the coolant is flowing with Tc naught. At any section the coolant has got a temperature Tc, here the reactor temperature is T and the diameter is D. So, temperature is going to progressively change along this z axis along with the change of conversion. So, we may think about the simulation problem where that is, if the inlet condition is given and if this is the length, what will be the outlet temperature and conversion. So, you see that we had a steady state, we have derived a steady state equation Q dot W dot S minus theta I Cp I cap Fa naught into T minus T naught minus delta H Rx naught at Tr plus del Cp T minus Tr into Fa naught into Xa. Now, if I take the derivative with respect to the volume, here the V is equal to 0, here V is equal to Vt. So, 0 equal to dq dot dV, and there will be definitely no star r, and here it is theta I Cp I cap dt dV into Fa naught minus delta H Rx naught at Tr plus del Cp T minus Tr Fa naught into dxa dV plus del Cp into Fa naught into Xa dt dV. So, that is the equation. In handout we have used a different formalism, but that is much better. So, you see this cannot be analytically solved, but we have to formulate the equation. So, what is important to note that we have to get a dt dV term, but there is a dxa dV. Now, design equation of PFR is what? This V by Fa naught equal to 0 to Xa dxa by minus Ra. So, if we take the differential, it will be dV by Fa naught into dxa by minus Ra. So, obviously, dxa dV is equal to minus Ra by Fa naught. So, and additionally we have this q dot. So, you see that if we look into that section and think of a differential element between V and V plus dV, here it is Tc, here it is T, right. And the area, heat transfer area, that is dA. So, dq dot is equal to U into dA into heat is given to the system. So, T naught minus T. So, definitely not T naught, Tc minus T, right. So, dq dot dV is equal to U dA dV into Tc minus T, and let us write it U into A into Tc minus T. Now, what is A? A is the ratio of heat transfer area to the volume of the reactor. And if it is a tubular reactor and its diameter is d, length is L, so the heat transfer area is pi into d into L, and the volume of the reactor is pi by 4 into d square into L. So, it is 4 divided by d. So, if I replace it, we will get U into A Tc minus T minus theta I Cp I cap dt dV into Fa naught minus, here you see delta H Rx Tr plus del Cp T minus Tr into Fa naught dt dxa dV. So, Fa naught into dxa dV becomes minus Ra. So, this will be minus Ra plus del Cp Fa naught xa dt dV. So, you have got now an expression for dt dV. So, obviously, it is theta I Cp I cap into Fa naught, the first element, and the second is delta Cp into Fa naught into xa dt dV, right. And yeah, that is all, yeah, dt dV. And this is equal to U into A Tc minus T minus delta H Rx not at Tr plus del Cp T minus Tr into minus Ra. So, obviously, we have got an expression dt dV equal to U into A Tc minus T minus delta H Rx not at Tr plus del Cp T minus Tr minus Ra, which is a function of xa comma t divided by summation theta I Cp I cap into Fa naught plus del Cp into Fa naught into xa. So, overall it is a function of t and xa, right. So, this is our first equation. And the second equation already we have derived, that dxa dV is equal to dxa dV minus Ra, which is a function of xa and t by Fa naught. So, now you see this, this is equation number 2, This is equation 1. Now we can change this dV as this A cross section into dz, right, where A cross section is pi by 4 d square into dz. So from these two equations we can solve, and we have to write, this is a typical initial value problem, can be solved by Euler implicit or explicit Euler or by fourth order RK method. Now we need an initial condition, right? Now we can write that Z or V equal to 0, T is equal to T naught, and XA is equal to 0. So with that, we can simulate how the temperature is changing along this reactor, right? And this is for co-current tubular reactor. If it is a counter current, there is another equation we have to derive, that is for the coolant temperature. Now see, for the coolant temperature, what will be the equation? So this will be coolant is losing heat, m dot c Cpc dTc is equal to, with a minus sign, heat is, it's losing heat, so U into dA, U into dA into this Tc minus T, right. So dTc by dA, dA now we can write it as pi by 4 d, it can be written as pi into d into dz, and you can change it to dV as well. So this pi into d into dz divided by pi by 4 d square into dz. Okay, no. This is pi by 4 d square into dz equal to dV. So if I replace this dz, so this is dz, so this is pi into d into dV divided by pi by 4 d square. So it will become 4 by d dV. So dTc dV equal to U, and 4 by d is nothing but A, this is A. So U into A Tc minus T divided by m dot C Cpc with a minus sign. So that's my third equation for co-current. So these three basically, and we need an additional condition that Tc equal to Tc naught as well, right. Now if it is a counter current, what will happen? It flows in the counter current direction, right. So it flows with a counter current direction. So now to simulate what is happening, if it is losing heat, right, in the positive z direction its temperature will increase, so there will be no minus sign. So negative sign is to be deleted for counter current, However, there is a problem in boundary condition. Why? Because at this end we don't know the coolant temperature. So, we have to assume something, right? We will assume something, we will solve this and we will check here what is the boundary condition basically. Z equal to L, Tc equal to Tc naught. So, we will start with an assumed value of Tc at Z equal to 0 and go back to here, right, and we will check whether it is matching with Tc 0. So, it is a kind of trial method. We have to repeatedly solve these three equations and from there we can predict the coolant temperature profile, the conversion profile and the reactor temperature profile, right. Now, you see that this equation or this reactor, if I operate adiabatically, what will happen? So, it is adiabatic tubular reactor. There is no coolant. So, Q dot equal to 0, right. So, this term is to be removed. This term we have to remove. So, we will have this dt dv equal to minus of delta H R x naught at Tr plus del Cp T minus Tr right into minus Ra divided by summation of theta I Cpi into Fa naught plus del Cp into Fa naught into Xa, and additionally we will have dxa dv is equal to minus Ra by Fa naught. So, this is the adiabatic system, adiabatic tubular reactor. Further, it can be simplified if del Cp is small, then we will have dt dv equal to minus of del Hrx naught at Tr into minus Ra divided by summation of theta I Cpi into Fa naught, right, and dxa dv is equal to minus Ra divided by Fa naught. So, that is the further and final simplification we can have, and again that cannot be solved analytically because minus Ra is consisting of a nonlinear Arrhenius equation term if it is simply first order irreversible or any order irreversible reaction, right. So, there will be nonlinearity in minus Ra, right, even if it is first order. Why? Because the temperature term is nonlinear according to Arrhenius model. So, this is the perspective of PFR with heat exchange, a tubular reactor with heat exchange, right. And additionally, we have discussed that this coolant's effect, the non-adiabatic, this non-isothermal one, that is a baseline, or that is the primary, not the baseline, that is the primary. We have started our analysis with that, and from there we have simplified it to adiabatic and further simplified where this contribution of change of temperature from the reference temperature in the overall heat of reaction is negligibly small compared to the standard heat of reaction at the reference temperature. So, that is all for adiabatic tubular tubular reactor with heat exchange. Now, we will think of CSTR with heat exchange. So, CSTR, as we know, it's a long parameter model. So, we have to write a gross balance, thermal balance over the integral control volume. So, it is tank reactor CSTR with heat exchange. So, you see that this may be the CSTR and we have a jacket. So, here we are delivering coolant. Its flow rate is m dot c, its inlet temperature is Tci, and it's moving out with the same flow rate and its temperature will be Tco. Here we are giving the feed which is Fa0, Ca0, etc., Fb0, Cb0, and its temperature is T0, and we are withdrawing the product at molar flow rate Fa, Fb, Fc, etc., and its final temperature is T. So, if I write, and a reaction kinetics is given, we know that. Reaction kinetics, which is a function of Ca comma T, that we know. Now, if I write the general balance equation, now see what happens. So, here 0 equal to, let's first write the original equation, Q dot minus W dot S minus summation theta I Cp I cap into T minus T naught into Fa naught minus delta H R x naught at Tr plus del Cp T minus Tr into Fa naught into Xa. So, here you see what will be the design equation. So, let us discuss first the design equation, and once we have the design equation we can further substitute here something. So, design equation is V divided by Fa naught equal to Xa by minus Ra. So, Fa naught into Xa equal to minus Ra into V, right. So, we can replace this Fa naught into Xa term by minus Ra into V because Xa is unknown, or it may be unknown. For simulation problem, Xa is unknown. So, we will discuss that. Theta I Cpi T minus T naught into Fa naught minus delta H R x naught at Tr plus del Cp T minus Tr into minus Ra into V. So, that is my equation, but before we go for the final form we have to replace this Q dot. So, Q dot you see is the heat given to the reactant, right. So, it is m dot C Cpc Tci minus Tco, right. It's heat given. So, it's, we will think its temperature is decreasing, actually it will be a negative term, and it's equal to U into A into LMTD. Now, LMTD here is Tci minus T minus Tco minus T ln of Tci minus T divided by TCO minus T. There is no question of co-current or counter-current. So, that it gives UA into TCI minus TCO divided by ln of TCI minus TCO, TCI minus T divided by TCO minus T. So, you see this TCI minus TCO cancels out from both sides. So, we have ln of TCO is unknown basically, TCO minus T divided by TCI minus T is equal to, we have changed the log, so it will be minus of UA divided by m dot C CPC. So, TCO is equal to T plus TCI minus TCO into exponential of minus UA by m dot C CPC. So, that is the TCO, right. So, this can be actually simplified in all real conditions because we maintain a high flow rate, a high coolant flow rate such that UA is much lower than m dot C CPC. Therefore, exponential term exp of minus x we can simplify as 1 minus x nearly, right, as x which is UA divided by m dot C CPC is much lower than 1. So, we have now this TCO equal to T plus TCI minus, sorry, this is TCI minus T, right, TCI minus T into 1 minus UA by m dot C CPC. So, the heat given by the coolant which is UA into, sorry, m dot C CPC, m dot C CPC, TCI minus TCO. Now, let us substitute m dot C CPC, TCI will be as it is. Now, TCO let us substitute. It is T minus TCI minus T 1 minus UA by m dot C CPC. Okay. So, what it gives you? It gives you this, and this first one will cancel out. So, this minus becomes plus, m dot C cancels out. So, UA into TCI minus T, and we write it further as U into A into TC minus T, where Tc is closely equal to the arithmetic mean of coolant temperature. So, definitely it is a simplification. You can go by this equation, we can find out for a given T, we can find out the TCO, we will discuss that. So, first equation is this, we have simplified it to this. So, with that, our final equation with that will be Q dot, and let's not consider, let's assume again this W dot S is much smaller than Q dot. So, we have 0 equal to Q dot, and Q dot is U into A into TC or AT rather, let us write it as AT, okay, it is better. So, U into AT U into AT Tc minus T minus this one, the summation of theta I Cpi T minus T naught into Fa naught minus, let us write it as delta H Rx at T into Fa naught into Xa. So, that is my final form. Okay. Now, we have to think two different problems. If it is a design problem, what you will do, and if it is a simulation problem, what is to be done. So, for the design problem, here we have to understand that for any chemical engineering problem related to some device, either it will be a design problem or it will be a simulation problem. So, for design, what will be given? Let us see the exact terminologies, what will be given to us. Let us say it is an elementary irreversible liquid phase reaction. Let it be an elementary irreversible liquid phase reaction. Right. So, the reaction is A giving B. And what do you know this? We know this Fa naught, we know Ca naught, we know K naught, the pre-exponential factor, activation energy, specific heat of A, this delta H Rx. Let us say this del Cp equal to 0 and theta I all are 0. It is a pure A which is used as a feed. Right. So, we have to find out the volume required for, so calculate, or additionally we have given this Xa, it is given. So, calculate V, the volume required, and the outlet temperature. Right. So, this there will be this minus Ra into V, minus Ra into V. So, and additionally we have this design equation, V by Fa naught equal to Xa by minus Ra, which is a function of Xa and T. So, you can write that as Xa divided by K, which is a function of T, into Ca naught into 1 minus Xa. Right. So, for this form we will use this. So, it is from here we can write the energy balance equation can be restructured as, upon substitution of Q dot, as 0 equal to U into AT into Tc minus T minus summation theta I Cpi T minus T naught into Fa naught, and this terms are 0. So, delta H Rx naught Tr into Fa naught into Xa. Right. So, what you can do, that switch that T terms to a side, like T here is negative, so U into AT, T here also it's negative, so plus summation theta I Cpi into Fa naught whole bracket T, it's equal to U into AT into Tc minus delta H Rx at Tr into Fa naught into Xa. So, T is equal to U AT Tc minus delta H Rx at Tr into Fa naught into Xa divided by U AT plus summation theta I Cpi cap into Fa naught. So, we know Xa, so we have to get T. So, if I write a stepwise algorithm, it will be something like this. So, it is the algorithm to solve the design problem. Step 1, calculate T knowing XAF and other related parameters. Right. So, from this equation we can do that. We can calculate T here, and definitely from the other equation calculate the volume. So, next is find out K, which is a function of T, that is the only problem here, and solve for V from equation 1. Solve from V. So, here we have to use this equation. So, that is the design problem, right, and the solution of that design problem. So, next we have to think of the simulation problem. So, how to solve for this simulation problem? So, here see it is a simulation problem, elementary irreversible liquid phase reaction, Fa naught, Ca naught, K naught, E, everything given, and given is the volume. So, you have to find Xa and temperature. So, that is the problem. So, you see we have this V by Fa naught equal to Xa and first order irreversible reaction K naught into e to the power minus E by RT into Ca naught into this 1 minus Xa, and that is also equal to tau by Ca naught. So, we can write this is K, right. So, Ca naught cancels out, and Xa we can write as K tau divided by 1 plus K tau. Why? Because this is Xa by 1 minus Xa equal to K tau. So, obviously, Xa equal to K tau by 1 plus K tau. So, now you see what is the temperature function e to the power minus E by RT into tau divided by 1 plus K naught into e to the power minus E by RT into tau. Right. So it's a nonlinear function xa, let's write it EB or MB. It's not EB, it's MB, it's obtained from material balance. Now we have this we have energy balance equation. Truly speaking, we have 0 equal to U into A Tc minus T minus Tc minus T minus Fa naught theta I Cpi T minus T naught minus del H Rx naught into Fa naught into Xa. So, Xa EB from energy balance, what we obtained? U into A into Tc minus T minus summation Fa naught theta I Cpi T minus T naught, that divided by delta H Rx, this shifted to this side, delta H Rx into Fa naught. So this is nearly a linear function of T. Why I am saying nearly? Because Tc is dependent on T itself, right? Tc is what? And truly, this term should be U into A into this or rather this m dot C Cpc into Tci minus Tco, and Tco is a nonlinear function of T. So that is to be replaced here. Or otherwise, this Tc is equal to Tci plus Tco by 2. And what is Tco? Tco is equal to Tci minus T, or rather T plus Tci minus T into this what we have got initially. Let me check just a moment. T plus, so T minus Tci minus T 1 minus exponential of minus U into exponent, not 1 minus, into exponential of minus of U into A T divided by m dot C Cpc. So Tco is a linear function of T itself, right? But we don't know T. Now if I couple this Tco here, so still it will be a linear function, I think, of T. Of T it will be a linear function. But that part we simply disregard, because the change of this temperature for cooling water is very small, as we keep a very high flow rate of this cooling water. So as a consequence, what happens? This Tci and Tco are close to each other, so we have an averaging, right, arithmetic average. And what can be done, that we will assume a T, and from there we will calculate a tentative Tco. So we will substitute it here. We will get an expression for Xa Eb as a function of T. Or if we entirely substitute it back here, coupling these two equations, still it will be a linear function of T. So Xa Eb XAEB from here, what we can confirm that XAEB is a linear function of T provided your del Cp is 0, right. Now, we have XAMB and XAEB. So, what we can do, we can directly solve graphically, or we can solve these two equations and find out the temperature. And what is a graphical solution? That here I will get some this T naught and all, right. So, it's starting from somewhere, but it is linear. So, this is XAEB versus T, and material balance has got a nonlinear functionality of temperature. So, it will be like this, XAMB versus T. So, this will give you the temperature and final conversion, right. So, we solve our problem of simulation, and this can be simultaneously algebraically solved as well, but this is a simple graphical representation, and we can see that this is the actual scenario there, that we can solve this by graph. If we plot the graph, we can get this XAF and T simultaneously, right. So, that is about the tank reactor with heat exchange, that is a CSTR with heat exchange. Now, we have a very important understanding to be covered, that is when we have an equilibrium reaction, right, and additionally it is an exothermic reaction. We know from thermodynamic equilibrium that, you see, again I am repeating it, that standard Gibbs energy change, or standard Gibbs energy change is equal to minus of RT ln K, right, minus of RT ln K. So, the derivative of delta G naught by RT must be equal to minus of delta H naught by RT square, and that is equal to minus of RT ln K. Minus of ln K only, right. So, this will be minus of ddt ln K. So, ddt of ln K equal to delta H naught by RT square. So, if we integrate it, ln K2 by K1 equal to delta H naught by R, and 1 by T square, the integration will be minus of 1 by T. So, here it will be 1 by T1 minus 1 by T2, and that can be further written as delta H naught. This is heat of reaction. Or T2 minus T1 divided by T1 T2. So, we know that already, that if delta H Rx is negative, that is exothermic reaction, Kc and T2 is higher than T1, then Kc or K2 is less than K1. That is, K decreases with increasing T, right. That is the typical quantitative form here of what we know qualitatively as Le Chatelier's principle. So, that is the typical Van 't Hoff isochore. Now, the point is that for an exothermic reaction, the equilibrium shifts towards the left if we increase the temperature. Right. Now let's think of a first order reaction. First order, for simplicity, first order irreversible reaction. So here it is minus Ra equal to K1Ca minus K2Cb, where the reaction is A reversible arrow B. Now at equilibrium, K1Ca equal to CAE equal to K2Cbe. Now you see initially this Cb naught equal to 0 and here we have Ca naught. So K1 into Ca naught into 1 minus XAE is equal to K2 into Ca naught into XAE. So Ca naught cancels out and K1 by K2 is equal to capital K, and that is XAE by 1 minus XAE. So K into 1 minus XAE equal to XAE. So XAE is equal to K divided by 1 plus K. And we have this relation that we can further simplify it as ln K divided by K1 is equal to delta H Rx of 1 by T1 minus 1 by T. So if I replace here, I will get a nonlinear function. See, this will be K1 into exponential of delta H Rx naught by R. We have discussed it in this problem of T1 minus 1 by T divided by 1 plus K1 into exponential of delta H Rx by R 1 by T1 minus 1 by T. So if I plot the graph of this XAE, XAE versus temperature will be a kind of graph like this. So the equilibrium conversion progressively decreases with increasing temperature. Right. Now we know that for adiabatic reactor, the 0 equal to minus Fa naught theta I Cpi T minus T naught. Let's say we are not going into the detail of this delta Cp and all. So delta Cp into Fa naught into Xa. So this Xa equal to summation Fa naught theta I Cpi T minus T naught divided by minus of delta H Rx naught, and Fa naught will cancel out actually. So it will be summation theta I Cpi into this. So this, what it means, that if I start from T naught and my temperature will increase, so this is the maximum possible conversion we can achieve. Right. If I start with a higher temperature, say this is T01, T02 and this is T03, or rather this is T01, this is T02, this is T03, and here it is XA1, XAE2 and XAE3. So what we observe here, that as if we start with a higher initial temperature, my maximum possible conversion progressively decreases, because when XA intersects XA versus temperature plot intersects this XA versus T, and that is the envelope of this maximum possible conversion, because this is the equilibrium conversion. So equilibrium conversion progressive, this is limited if based on my initial temperature. So what is the strategy? From the engineering point of view, what will be our strategy to increase this conversion? We will use staged reactor with intermediate heater, right? For exothermic reaction, for exothermic reversible reaction, we use staged reactor with intermediate heaters. What is that? Say we will use reactor 1, a small size reactor, reactor 1. Next we will intermediate heater, intermediate coolers. So next we will use a cooler 1. So its temperature decreases. I will show you what will be the reflection in this plot. Next, this is reactor 2, another cooler C2, and this goes on, right. So this XAE versus temperature. Now you see, this is my equilibrium curve. So this is XAE versus temperature plot, right. Now start with a high temperature. This is T0. So we go up to this, far away from this equilibrium. Next we cool it. And again it enters into, so this is contribution of R1, this is C1. Again we go for R2, we go for C2. Next again we go for R3, C3, and so on and so forth. So we can reach a very high conversion even for this exothermic reversible reaction, where my final outlet, instead of using a low temperature feed, right, even if it is possible lowest temperature feed, still you can go here, but if you use intermediate cooler, so you can do this and you can go for a very high conversion, right. So that's all for this thermal perspective of the reactor. In the next session, we will discuss about the non-ideal reactor, how to track the non-ideality by conducting a simple experiment called residence time distribution experiment, and therefrom how we can model this non-ideal reactor. Thank you.